Hey everyone, it's Twisty Fox. So what you're watching right now is a method that my program created going against CFOP. Now, as you can tell, with the method that my program created, it is building blocks in a way that kind of makes sense to a human. It's not doing the optimal algorithm, and it is a human solvable method indeed. In the end, it is able to beat out CFOP, which I think is amazing. So if you just want to get the high level from this video and you don't need to go into the nitty-gritty details, that's the takeaway. My program is able to generate methods that are, in theory, better than real human solvable methods. Although I will say there's a bunch of caveats, of course. There's a reason that I have not started using this method personally, but we'll get into all that in the end. And I won't be able to cover all of it in this relatively short video. So if you have any follow-up questions, I encourage you to watch the video and maybe look through the code if you want to, and then ask me any questions because I'm happy to talk with anyone about this. So what is this at a high level? My idea is that I think CFOP is a good method, and there's a reason a lot of people use it, but considering how many combinations there are in a cube, I have a theory that there's a better human solvable method out there, and this program aims to help try to speed up the process in finding them. I've taken a lot of different methods, some that are human written, some that are randomly generated, some that are mutations of human generated methods, where they resemble methods such as Roux or CFOP or even CZ, but some pieces are changed around. I have thousands of these, and with each of these methods, I've generated some solves. I've taken all of this data and found ways to quantify it so it can be parsed by a machine learning algorithm. In this case, I've done the random forest algorithm. It's then learned how to take these methods, and with the features that I've extracted from them, it tries to predict the score, the end of what is the best method. In theory, if this oracle is 100% accurate, you could put in every method that you could ever think of, and it will output the method that performs the best. Now, it's not quite reached that theoretical greatness, but it has reached a point where it will predict if a method will do better than CFOP or Roux, and quite accurately. The comparison you saw in the beginning was just one random method that was predicted to do better than the vanilla Roux and CFOP, and as you can see, it did. Furthermore, what makes this really interesting, this method in particular was generated was not part of the training data. I've not just trained on a bunch of methods and it's learned to pick out, well, this one I remembered is better than Roux. No, this one was actually one that was generated, but I'm going to get into all of this. So here's going to be the different parts of the video. Firstly, I'm going to talk about the method solver. To get all this data and everything, we need to have a way to solve cubes with any abstract method. So that's the first thing I'm going to be talking about. Secondly, I'm going to be talking about generating all the data in general. There's a few interesting things I had to do, and I've already kind of touched upon it, but I'm going to go into more details there. Third, I'm going to talk about machine learning a little bit and how I was able to use the random forest algorithm to take the features of methods and predict a score from it. And finally, I'm going to show how we can use this machine learning oracle to do a search for better methods, which is basically what I had to do to get that one method that I showed you at the start. One more thing that I do want to talk about before getting into this is AI usage on this. And I want to be completely transparent with the fact that I did use a lot of AI to help write this code. This project was for a class, and my professor did allow this. It's part of the policy. I was not cheating at all. And everything in the end is from my ideas and things that I thought of. And I think regardless of whether a human wrote it or AI wrote it, the results speak for themselves. It's able to find methods that are better than what's currently available. So just keep in mind that I didn't necessarily write every single line of code myself, but I did engineer the entire project at the end of the day. All right, with all that out of the way, let's get straight into the video. Okay, so I'm going to be on my terminal just because that's what's easiest for me, but you don't have to understand everything. I'll just point out what is important to know. So firstly, over here on the left, I have what is the abstract file type, the DSL for a method. And I have CFOPs pulled up over here. And basically, this is the type of file that defines what the CFOP method is. So let me point out a few important parts. At the top, you write out the method's name, and you can specify a few flags. I think I have these documented somewhere. The only one I have right now is the rotation. So that basically means I want to start every solve from an X2. So obviously it scrambles the cube with the same orientation as WCA, which is white on top, green in front. I want to have yellow on top and blue in front. So what I've done is just say do an x2 for every solve. And I'll show you what a solve looks like in a little bit, but it'll basically do an x2 for every solve. Then everything is either broken down into steps. So as you can see, I have a step here, or groups of steps, which is something like this. So first let's talk about steps. And that's basically going to be something like a cross, where, for a cross, you have 4 pieces that you need to solve. And it's just going to find the best way to solve those 4 pieces. So what you can do to specify to add pieces is for edges, you write add edge, and then you type the edge you want. So these are all the U-layer edges for cross. You also must start with init empty cube. That's just so you start off with the empty cube and then build up to everything. So that's for the cross. Now there's groups of steps. So basically, if a cross has 4 edges that can be solved in any order, a group of steps has 4 steps that can be solved in any order. So each step is a F2L pair. I just have the names written out for them over here. And you can specify the order you want them done in. There's a few different orders, such as best overall, which will find the most optimal way to solve F2L. Right now I have best 1, which means that it looks at which F2L pair at the moment is the most optimal, and it solves that one. Kind of similar to what you would do if you're doing a CFOP solve. If you see there's a 3-move pair, you're going to do that compared to the 8-move pair, even if that 8-move pair happens to lead to the rest of the pairs being 3 movers. You might not necessarily see that. You can also specify like best 2 or best n. You can also specify worst n just for fun. There's a lot of different options, but that's basically the main idea. So over here is OLL, and what I've done for OLL is just add corner orientation, edge orientation, pretty simple. And I also have this flag over here, which is cache algorithm. So what this will do is for every time it runs into an OLL algorithm that it tries to solve, once it solves it, it's going to write it into a file. Then next time it reaches OLL, it's going to check for all the algorithms in the file to see if it happens to be the right algorithm to solve it. So if it's the right algorithm to solve it, then great, it will use that. And if not, then it's going to actually search for it. And then once it finds it, it will write it to the file. So after doing a certain amount of solves, you will have all the OLL algorithms in the file. Now, I know this is not the most efficient way to do things. I think in theory, I would love for this to become eventually a hash table where it can search up from there. I've just not gotten around to writing this where it's the optimal way, but even as it is right now, it's good enough. And the free layer is D basically means that for every algorithm, it tries all combinations of doing a D before it, D after. And why it's D is if you are going to do white cross, then D is the layer, the bottom layer. So we'll basically try D2 algorithm, D algorithm, D prime algorithm, just pure algorithm. Basically all combinations to see if any of them work to solve it. And then finally I have PLL, where I've just added the rest of the pieces, and that's it. So let me show you what it looks like when we want to solve with it. Okay, let's run this. And it's generated a random scramble. Give us the solution. So let me go ahead, copy and paste this over into Twizzle. And let's go through this. We don't have to look at every move, but just skim it. So as you can see, cross is solved. Solved the front left pair, front right pair, back left pair. What all case did we get? We got the H case. So let's see what it does. I think that's the optimal algorithm. And then PLL does some weird PLL that I came up with. But you get the idea. It was able to do a CFOP solve. Let's do another one. I don't know, like Roux. So it did Roux. And we could have specified to do the same scramble. Doesn't really matter a whole lot, unless if it's comparison purposes. And it's going to do Roux. Solves that block. Looks like it almost solved the whole Petrus block. And yeah. So you can pretty much write any method that your heart could dream of, as long as it falls within these constraints. Some methods you can't really write. For example, I can't think of a good way you could write heis. I'm sure you could write some abstract syntax where you could figure out how to write heis, but this is a little more primitive, but still it can encapsulate all the big methods. So if you're curious how this works under the hood, I use another program called CubeSolver, which handles the solving logic itself. CubeSolver takes in some constraints, similar to how I have add edge, add corner. I think that's actually where I got the syntax from. It takes in those constraints and it takes in a scramble. That's all it takes in. It can't solve the whole method. But if you play around with it, you can actually turn it into the method solver. So the first time around, let's say for CFOP, you will say the scramble is the scramble and the constraints are the cross. That will produce the solution to the cross. If you want to solve the next pair, you will specify the constraints to be cross plus 1. The scramble will be the scramble plus cross, and the solution will be the pair. You can repeat this process and it will solve the entire method. As for doing things like finding the best solution, it tries all paths and then just outputs the one that will happen to be the fewest moves. And similarly for worst and so on and so forth. So that is how we solve cubes. And I think that alone is pretty cool. I encourage anyone, if you want to mess around with it, try it. I had a lot of fun with doing this. But let's go on to the data generation parts now. So I have a few things here where you can generate either the mutations of methods or random methods. So let's first run like the mutate methods, or not. Let's first randomly generate some methods. And it'll take a second, but yeah, as you can see, it's generated. Now let's try mutating them. Oh, I had a typo earlier. That's why. Yeah, so one thing that it does that is important to note is there's different workspaces. I've not prepared a demo for this, but let me show you real quick. So if we go to workspace, I have all these different workspaces, and these are basically different sets of algorithms. So for example, I have stable. So if we do tree stable, it basically is stuff that is methods that you'd want to keep around forever. APB, because I was messing around with that, CFOP, Petrus, Roux, ZZ, etc., etc. I also have a lot of ones that have temporary files or junk methods that we don't care about. So let's go ahead and look at that real quick. And this is going to generate a lot of gibberish, so just hold on to your horses. Yeah, as you can see, a lot of random methods, just junk that we don't need. Anyway, this is how we generate the methods. And I kind of showed this already, but this is what the structure kind of looks like on the inside. So for example, there's algorithms. So if we go to algs, let's look at some of the CFOP algs that's generated. Go to CFOP, and then let's look at the top few. Yeah, these are some CFOP algorithms. So if we go over here and test to see what this does, it is just some OLL. So I guess I found this OLL at some point, and I wrote it down, and now when trying to solve OLL, it sees if it can find that. There's also the raw data, so let's look at that. This is where the solves are, and the DSLs are here, the different methods. So let's look at, like, I don't know, just this random method. And this is some method that's been generated. I don't know off the top of my head how good this method is, but we'll get to that later of how we can determine how good these methods are. So that's pretty much how the methods are generated. You just run these a few times, mutate the methods, generate random methods. If you wanted to sit there like a monkey and type 1,000 methods by hand, you could. If you wanted to get Claude to write them all, you could do that. Just make sure that Claude actually knows how it works, because surprise, surprise, AI does not really understand how cubes work. You have to be very careful. I have learned as someone who used AI on this project. So I think it's a good time as any to go ahead and show what the config looks like. And there's a bunch of different stuff here, such as the workspaces, the solver. I should have probably mentioned this in the previous section, but you can have it so that there's a cache timeout. So what I think this does is it tries to search for this many seconds to see if it can find a solution without having to look through the cache. Otherwise, it looks through the cache of algorithms. There's a bunch of different stuff, but included in here is some of the data generation stuff. So this is what matters for right now, where it will generate 10 scrambles. And there's some other stuff that we don't need right now, such as how many total generate. So to generate the data, we're just going to run this command over here, and that's going to generate it to that workspace. As you can see, it doesn't really matter where you generate to, but we're just going to generate like this. And I'm going to tell you already, this takes a long time. We're talking days of running on the school's computer. So this, I'm still somehow have access to my old school's computer. Right now, it's just complaining because I've already done stuff with some of this, and so we don't really need it to do anything. But basically, what you would get normally is it would start solving each of these methods 10 times. I also have set up so it can do parallelism. Let me show you in the config. As I showed you earlier, it spawns those cube solver processes, kind of like a thread pool situation. I guess it's not multi-threading, it's multi-processing, where it spawns as many of these as you want. Those are where it really gets hung up at. So you can basically extend this to like infinity. I can easily take up 400 gigabytes of memory that are on these school servers, and I could take up more just because these processes do need a lot of memory. I think on average you can expect to solve one method, you will need around 30 gigabytes of RAM. That's just because to find an algorithm, it takes a lot of depth to find it. But anyways, I digress. That is basically what I've done to generate a lot of solves. So we have a bunch of data now, and I've shown you a lot of what the stuff looks like. I have all of this stuff over here where it's just a raw method file. And I probably should have shown this earlier, but I have solves that are recorded in CSVs. So let's look at, I don't know, like the ZZ one. I love ZZ. Very hard to read, but basically this is a CSV or an Excel type file where each different column separated value is a different step for the method. So for example, this is the scramble. From here till here is the EO line, etc., etc. Looks like they got pretty lucky here, as those 36 moves easy solve. Pretty cool. So that's what the raw data looks like. But this is nonsense. Like, especially for us, I mean, it looks like we're in the freaking Matrix right now. You know, with all this stuff just up on our screen. This cannot be easily parsed. So before it goes to machine learning, we need to find a way to parse this. And that's where extraction of features come from. So let me go ahead and show some of the extracted data and what that looks like. Okay, yeah, I just had to spend some time finding this. Let me break all this down for you. Okay, so take a look over here on the left-hand side. And basically, all of this is stuff that has to do with the solves themselves. Now, all this data over here, except for the score, can be used to determine the score in a custom scoring function. Basically, you are given access to all this information, such as how many moves it takes, how many steps, how many solves, and you can write any Python function you want to score. So let me go ahead and pull that up, what that actually looks like. Okay, yeah, so right now this is literally the lines of code that score it. I forget exactly what it is, but looks like it gets the average moves, and then it needs the average moves to be valid. And then once it gets beyond this threshold, it gives it extra penalty. Basically, if a method is able to do lower moves in total, then it's going to get a better score. However, there's a penalty where if steps are taking more than 7 moves, then it's going to be heavily penalized. So this is just a scoring function that I have written because that's what I wanted to focus on. I wanted to focus on solutions that were both efficient and each step was a reasonable amount of moves. Before, when I was purely optimizing just for a low move count, it was producing solutions that were insane, like 12 move steps, but there's only 3 steps, and it said this is the best one, and that's not human solvable. You cannot predict 12 moves for an average step. However, this is what I got to produce that method that I've been talking about this whole video, and it does pretty good. Again, this is just nonsense, but it just takes in all of that data and computes it and gives the score. So over here also is the raw data for each method, and it's able to quantify different statistics, such as the number of steps, how many groups of steps there are. There's a lot of stuff here. One thing that I don't know how to find on here, but there is a statistic that tracks within a step how many pieces share a side. So this will give a bonus to things like Roux, where you're building all these blocks, and it will just give it a number. The number doesn't necessarily mean a better score, but it means something. And it's up to the machine learning algorithm to determine if those higher numbers tend to correlate with better solutions. So I've gone on this big tangent. It takes in all of this data, and then it tries to predict the score. The score is computed from this data, and it's over here. And that's where the machine learning comes in. So first we're going to train it right now. And these are the different things that it found. Honestly, I'm fuzzy on a lot of the machine learning part, the one thing that this project was supposed to focus on. But it does use random forest, which is a machine learning algorithm that, if I remember right, anyways, back from that tangent, these are basically the different parameters that define it, and it's able to learn it. So we learned this. Let's evaluate it right now, see what it does. I think right now it only has these methods, but it says the error from the actual versus predicted. And as you can see, they're within the right ballpark. So beginners has the most errors, didn't predict it accurately, but CFOP, with the way that it's predicted it, very close. And somewhere, I forget exactly where this was, I had it take the percentage off for each method of all the random of thousands of methods. It turns out on average for all the methods, when they're all put into the machine learning model, the actual values compared with the predicted values, it turns out each of them are around 10% off from the real value. So in some sense, 10% is like, wow, that's not going to capture all the fine detail. But in another sense, like, that is crazy. It's that accurate. I mean, when you're talking about numbers this small, especially, like, I think that's really cool. So 10% on average is what we can get with random forest. I think with linear regression, when I tried that, it was around 20%. So there's some correlation going on. But yeah, within 10% is generally what we can expect. So basically, this is one of the end goals of the project. And for my class, this is what I touted as being like the big thing we're going for. And yeah, it's really cool. Basically, from all the data generation that takes so much computation and time, we're able to make it into a pretty simple machine learning model where we can put in a method, take those different features, and get the score to however we've defined the score. So what can we do with this? Well, we can do a search for better methods that uses that as a rough guess. So what I think the algorithm is, it's something along the lines of take some amount of methods, let's say 250 methods. I think that's what it's set to be right now. And out of those, put them all through the model and get their scores. Rank them from best to worst, and then take the top one from that, the one that's ranked to be the best possible method, and get a bunch of mutations of that. So for example, at the start, Roux might be considered the best method. So what it's going to do is it's going to take a bunch of mutations of Roux, different variations of it. It's going to put those back into the pool, going to sort them, and then we're going to have some mutations of Roux. Some of them might actually be higher than Roux. And whatever is at top, again, it's going to generate more mutations based upon that. I think there might be a few different edge cases, but that's the general idea of how this works. Once it's generated sufficient number of these, it's going to take the top, I think 20, and actually compute the real scores of what they would be. It's going to generate real solves with these methods. And let's go ahead and run this right now, see what we can get. Yes, I'm going to let this run. It might not finish, but that's basically what it's going to do. And in the end, we're going to see some results. So I've already run this before. Let me pull that up. Okay, yeah, so while I'm getting this up, as you can see, it's generating some of the methods, 10,000 of the Oracle scored methods. And I'll let this run over here while I'll show you this. So basically it has these different methods, all the different candidates, the different results of them scored. I think there's something where they all converge to be the same method, and with the scoring function, this is like the best that could possibly happen. Probably need to look into that, but they all are ranked pretty darn high compared to the other methods. And here I have it where it's taken these methods. Again, it kind of looks like they're all the same, but it's predicted to be good. It's actually a little worse than it predicted, but around that range. And the move count, 40.2 moves on average, with 6 steps, 6.7 moves per step, which is a decent amount. Like, that's not bad. If you remember, we're trying to optimize for having steps less than 7 moves. If we really made there be a big penalty above 7 moves, that's probably why it converged near to 6.7. And so over here, it's doing more of this, just evaluating those top few candidates. And so while this is loading, I want to talk a little bit about the limitations of what I currently have. I think I've been very clear that this is not the end all be all, but obviously there's only so much you can extract from these method files. They can even capture a full complex method like heiss. So how are you going to be able to quantify heiss? And the different statistics about how good a method is, like what's written down, I don't have anything that accounts for how ergonomic it is or anything. So anything that's better or worse is not taken into account at all. But what's interesting is you could do that. You could find out some way to quantify how ergonomic a method is. You could find something that quantifies anything you could think of. If you could think of a way that you could write code for it to quantify, you could incorporate that. And so I think that's really cool. I think that there is potential here if someone else wants to mess around with it. I think my time with this project is about done, if I'm being honest. I spent a whole semester working on it. I had so much fun. I got a really cool result in the end, but I don't think I'm going to do a whole lot more. But I just want to share this with the community because I thought it was a really fun project, really novel project. I've not heard of anything like this at all. So I thought it was really fun to come up with my own idea and do something really novel like this. And one more thing that I thought we should do is just do a live experiment to see how it performs against CFOP. So this is the one that was ranked really high, and I've generated a solve. Let's just generate a new one. Okay, so here it is. Looks like, I think it does EO earlier on, so that's why this EO step is considered to be done already. So we have this over here. Let's also just take the same screen build and do a CFOP solve with it. So here's the command to run it for CFOP. And let's put these both into Twizzle. So the generated method had 43 move solution. Let's make sure that's correct. It is correct. Cool. Let's check for CFOP now. And CFOP's 55. So obviously this is a Roux mutation. Maybe let's try against Roux. Looks like in this case for Roux, it's 48. So it was able to find a method that's technically more efficient. Yeah, another data point for how it is actually a method that is more efficient. So one thing you might be wondering is, what is this method that is so good that it generated? Now, again, I do want to say that it might not actually be better in terms of the metrics that I have defined for it to be good. It is better. One of those primarily being move count. Having said that, let's take a look at what this method does. So first, it looks like it does EO along with a corner and an edge. So let's go. It's labeled as being first block because that's the first step of Roux, and it's a Roux mutation. But obviously it's not Roux, so it does EO and then solves this corner and this edge. Interesting. Then it looks like it solves another corner and another edge. So let's go ahead and check that out. Okay, so I guess it first solves these two pairs along with having edge orientation done. Let's check out the back left block. So it looks like it adds a bunch of edges and then some corners and another edge. The step is kind of long. Yeah, so it looks like it basically finishes off the Roux blocks. So basically, solve the first two Roux blocks, but solve them in a weird way and do edge orientation. Then do CMLO and last 6 edges. So even going through this, I can tell that there's obviously some biases. I think it gets a real big boost in average move count because edge orientation is marked as being 0 moves and that counts towards the average, and so it brings that these ones that are a little bit longer down. So obviously there is room for improvement, but still, even with that, it is doing better than Roux and CFOP. Vanilla Roux. This method where you solve this edge in this corner does better. I just think that's pretty interesting. So in summary, what I've done, I've used machine learning to predict how good a method is. With this, we can do different things, such as comparing a bunch of different methods and seeing which of them does the best. And we can obviously evaluate that. We can do a lot of fun stuff with this. So overall, I'm really happy with how this project turned out. I thought it was really fun. Let me know what you think about this. Is there any other use cases of this that I've not thought about that you can think of, or any other metrics that you think could be really useful for quantifying the cubes or quantifying the solutions? Let me know all below. I'm really curious to hear your thoughts. But thank you so much for watching, and I'll see you guys in the next one. Bye-bye.